This presentation is going to be a simplification of the presentation in the OpenStax textbook. I'm going to skip nearly all of the emphasis on calculus that's in the book, probably all of it. We don't need that. We're going to be considering situations where we have either zero acceleration or constant acceleration. And we're going to look at a two-dimensional presentation instead. What you'll learn could be extended to 3 dimensions, but we won't be using that for now. There will be a couple of situations later in the year where we might extend things into the 3rd dimension, especially when we get to magnetism. But we're going to just stick with a 2-dimensional presentation. And the first thing I want to present to you is a key idea, and it may seem very simple, but it's going to guide everything that we do. First of all, let's imagine that we have 2 vectors. E is going to be E sub x along I hat plus E sub y along j hat. And E sub x and E sub y could be things that change with time. They could be positive, negative. They can be all kinds of different things. So this will extend to all sorts of vectors. And then we'll have a vector x that's going to look very much like E. It'll have an x component. Whoops, that's supposed to be an f sub x. And it'll have a y component. And so same conditions for vector E. Now, if E is equal to f, that means that E sub x along I hat plus E sub y along j hat will equal f sub x along I hat plus f sub y along j hat. That seems like a simple idea so far. If that's true, then the following is true. Then the x terms on the left side must equal the x terms on the right side. Then the y terms on the left side must equal the y terms on the right side. This seems like a pretty simple idea, but it's going to let us do some fairly powerful things when we're working with 2-dimensional motion. We can extend this to more complicated equations. If we have a vector expression, for instance, we have that a plus b is equal to c plus d. And these can get relatively complex. For instance, let me write down some expressions for A, B, C, and D. Okay, we have A is equal to A sub x along I hat. It doesn't have a j hat component. B is equal to B sub x along I hat plus B sub y along j hat. It has both an I and a j hat component. C is equal to C sub y along j hat. It has no x component. And then D has D sub x along I hat and D sub y along j hat. Okay, I could have all sorts of mixes of things going on here. And what I would end up with, the I hat terms from the left side have to equal the I hat terms from the right side. Well, I've got an addition going on between A and B, so I'm just going to pick off the I hat terms. And I'm going to do this. I hat terms. Whoops, terms. Well, I've got an A sub x, I've got addition, and I've got B sub x. Okay, that's the I hat terms from the left side. Those have to equal, because this expression is equal, they have to equal the I hat terms from the right side. Well, on the right side, I've got C, but it has no I hat term, no x term. D does. So A sub x plus B sub x have to equal D sub x. Okay. If I consider the j hat terms, J hat terms, let's see, I only have one on the left side. I just have b sub y. So b sub y has to equal, what have I got on the right side? C has a term, c sub y. D has a term, d sub y. So that gives me these two equations, but these are scalar equations. We know how to solve those. That's just ordinary mathematics. But this is something that we can do. And we'll find out that there is an independence of perpendicular motions that let us get away with this. And we'll be considering one equation for the x term, one equation for the y term. And that's what we'll be able to do with these things. So let's extend this to the idea of position and motion. And let's let r be our position vector. And it's going to equal x in the I hat direction plus y in the j hat direction. X and y may be functions of time. In fact, for us, they are going to be. They're going to be changing in time. That's what makes this stuff interesting. Okay. Then we'll have a velocity vector. Actually, we can have an r naught vector. Okay. This will equal x naught in the I hat direction plus y naught in the j hat direction. Some of these things might be zero. Some of them could be positive, negative, all sorts of different possibilities. But in general, this is what it could look like. Okay. Now, let's suppose we have motion with constant velocity. Okay, so we would have v is equal to v sub x in the I hat direction plus v sub y in the j hat direction. So that's what v happens to be. Well, here's what we can write. We can say r is equal to r naught plus v as a vector times t. Look at the equation that we get out of this. If we consider the I hat terms from this, on the left side, I'll have x. That's it. On the right side, I'll have x naught plus v sub x times t. That is the same as our equation for constant velocity. That's what we have in the x direction. For y, we'll have something similar. We'll have y naught plus v sub yt. And we can solve these things independently, given the time, knowing what v sub x and v sub y happen to be. But these are scalar equations. And we actually have two scalar equations here. If we have two equations, we can find two unknowns from that. So that's something that we'll be able to do. Now let's extend it to the idea of having acceleration. And I'm going to take it straight to the situation we're going to have where the acceleration in the x direction is equal to 0, and the acceleration in the y direction is going to equal minus g. And the equation that I'll be able to write down for this, the mixed equation, will look like this. R is equal to r naught plus v naught as a vector times t plus 1/2 the acceleration times t squared. Let's imagine here for our initial conditions, we're given that v naught has both an x and a y component. So we've got v naught x in the I hat direction and plus v naught y in the j hat direction. So that's what v naught happens to be. R naught maybe in this case we have an x naught that's part of r naught in the I hat direction, but y naught is equal to 0. And so we don't have a y naught. And I'll just put that in parentheses here. Y naught is equal to 0. Okay. That could be, it depends on the description of the problem that we happen to have. Okay. Well, what does this equation look like if I just consider the I hat terms? Oh, r is our usual value of r. It's going to be x in the I hat direction plus y in the j hat direction. What do the equations look like that I get here? Well, v naught x, there's no acceleration in the x direction, so this is the constant x. And I'll just pick things off. Take the I hat part of r, that's just going to be x. Take the I hat part of r naught, it's going to be x naught. Take the I hat part of v naught, well, that's going to be v naught x, and it multiplies t, as I can see in that equation. There's my x equation. Okay, that's a constant velocity equation. Now let's do the same thing for the j hat terms, the y parts. Pick off the y part of r. I'll have y equals, well, there is no y naught, so I don't have that term. What about v naught? There is a v naught y, so it will equal v naught y times t, and the a sub y is minus g, so I'm going to get a minus 1/2 gt squared. Now, if there's constant acceleration, I can get another equation out of this. I can have something that looks like this. V is going to equal v naught plus at, but v naught is a vector and a is a vector. And if I pick off the x part of this, the I hat part, well, v I haven't defined yet. V as a changing time, it'll equal v sub x along I hat plus v sub y along j hat. So with this equation, I pick off the x parts, and I will get v sub x is going to equal, well, there is a v naught x. Okay, now pick off the x part of a. There isn't any because a sub x equals 0. In fact, I could write this. A is just going to equal minus g in the j hat direction. So that's what I get for the x equation for velocity. It's constant. Whatever it is at the start, it stays that. But what about for y? I would get v sub y, okay, that's the left side of the equation, will equal v naught y and let's see, plus at, the j hat part of that, which actually gives me minus gt. And turns out these are the equations of motion for projectile motion. That's something where x is horizontal, y is vertical. The only acceleration going on is in the y direction, so v sub x is constant, and those are the equations we have to deal with. Okay, this one, big deal. That just means this is going to be a constant. But this is just a linear equation. This is going to be easy to solve if we know the value of t. This, maybe it's a quadratic equation. In general, we would have a y naught tagged on to that. For the particular thing that I made up, plus, the particular one I made up, we didn't have a value for y naught, but if we just added a y naught to that, we'd have the general expression for projectile motion. And every time you recognize a problem as projectile motion, you start off with that. So let me fix that last equation. It should look like y is equal to y naught plus v naught y t minus, yeah, I had a t on there, minus 1/2 gt squared. And just substitute this one in for that one. Maybe y naught's 0. If something's launched from ground level, that would be the case. But that's the set of equations for projectile motion. And that's our first look at two-dimensional motion, is that. So next thing we'll do is start solving some projectile motion problems.